So now we're going to use antiderivatives to determine the area under a curve. And let's see why that happens, or how and why. Why and how. All right, so let's say I've got some curve y equals f of t. F of t. And I want to figure out the area from A to B. So we want the area under f of t from A to B. And what we're going to do is we're going to define a function, a of x, such that a of x is the area. So define a function such that a of x is the area between t is equal to a, t is equal to x, the t-axis, and y equals f of t. So t equals a, t equals x, the t-axis, and the function. So a of x is a function that calculates the area. Okay, function that calculates the area. And we want to find out what that function is, right? What is a of x? And we don't really know too much about it, but to figure out a of x, we're going to start off by finding its derivative, hoping that that will help us. So to find a of x, okay, and that might not seem too obvious yet, but we'll see that it actually will help us. Okay, so we don't know anything about a of x. We're going to use the definition of derivative, right? So we know the definition of derivative, going back to first principles. So the derivative is the limit as h approaches 0 of a of x plus h minus a of x over h. And what's that look like then? Okay, so let's just take a slice of this so I can draw it out reasonably the same. So let's take a little slice of this, right? So here's x plus h. This area in here is the area of x plus h minus the area of x, right? So we know the function says it's the area from a to x. So this is the area from a to x plus h minus this area, giving us this little slice here. Okay, and we're going to use a rectangle to approximate that. And if we make h really small, then the rectangle is going to have a height of f of x and a width of h. Okay? So, when h is small, let's say this. When h is small, then this area is approximately the rectangle. And we use use rectangles to approximate areas, if you remember. Shown. Whose height is f of x, right? So the height, we're going to approximate this by a rectangle. This height, remember this is really, really small. It's not kind of drawn big, but this will be really, really small. It has a height here and a width of h. Okay, and width h. So squeeze that in. So we go back up here, right? So a prime of x, which is the limit as h approaches 0 of a of x plus h minus a of x over h, which is the limit as h approaches 0. So the a of x plus h minus a of x is this rectangle, right? F of x times h. So its area is f of x times h over h, which is the limit as h approaches 0 of f at x, which is f of x. And so that is why we want the derivative of that. So the derivative of the function, right? The antiderivative is the area. All right, so right. All right, now let's just summarize this. So if we plug in so remember the original function was y equals f of t. If we plug x in for t in the original function, which was y equals f of t, extend the page.
In what?
In for t.
Oh.
If we plug x in for t in the original function, which was y equals f of t, we get f of x, which is the derivative of the area function, right? Okay, so that's why the antiderivative is the area. Okay, give me a moment. All right, so now we say, so a of x is one of the antiderivatives of f of x, but which one? Okay, so when we first looked at antiderivatives, we said there's a family of curves, right? All of which have that particular derivative, right? By adding a constant. So we're going to start off by saying, assume capital F of x is one such antiderivative. Okay, so we know there's a family of antiderivatives. We're going to assume that capital F of x is one such antiderivative. So the derivative of f, capital F of x, is f of x. Well, what does that mean? Okay, so that means that a of x, the area function, is f of x plus c, right? It's a particular antiderivative plus some constant. We can always add a constant, right?
Do you have to add a constant? Or
Yes.
Could your constant be 0?
Yes.
So it could not.
Here, you're going to see. Watch what happens. Okay. Now, what did we define a of a as? The area of just the left-hand side, right? Here's a hint. No. Look at it sideways. 0.
Shoot the 3-point.
Yeah. Aren't the Raptors sad? I mean, come on.
That was kind of low.
And the Blue Jays too. Like, I mean, they're blowing 6.
Playoff hockey.
Yeah. Well, and the Leafs, they're just totally out of it. Remember A of A? What's A of A? 0, right? They make the playoffs. I know. I'm just saying Toronto's a sad sports city.
Big surprise.
Okay? So, if A of A is 0, but A of A is also f of A plus c, right? You put an A in here. So A of A is 0. So 0 is equal to f of A plus c. So the particular constant is negative f of A. Right? So that constant, the constant we want to add is negative f of A. All right, so the constant, right? So that means that A of x is equal to f of x minus f of A. Right? So A of x, okay, what's c? C is negative f of A, right? So c is negative f of A. We come down here, go back to the original. Now we figured out what c was. We replace it with negative f of A. But what we really want is A of B, right? We want the area from A to B, and that's defined as A of B, which will be f of B minus f of A. B, the other end, the right-hand side. So when we say A of B, right, A bracket, B bracket, this, we're talking about the area from A to B. Not to B. That is the question. Okay. Now, I mean, basically, you can look in the book has a particular example where it says find the area under something. It's in the section that you're going to be doing the homework in. You can look. It's example 2. And it says find the particular area, and then it says, well, we got to figure out what C is, so we can do that. But really, what you can think of it is whatever that C is, the constant is, it'll be added on and then subtracted off, right? So it doesn't matter what the constant is. Okay. So, well, it does. It's negative f of A, and that's what does this. Okay, so if f is any antiderivative of the positive function f, remember we're finding the area of a positive function, right? Area above the x-axis. So there's your formula you're going to use, right? The area of B is f of B minus f of A. Okay? And let's do a few examples, and then we'll have time to work on some for the test next Monday. Okay, this coming Monday. Not today. See the snow? It should be gone by then. Or not. Yeah, I know. No. All bets are off. It's starting to go away a little bit. But find such determinants. Okay, so determine the area under the curve x squared plus 2x on the interval 3 to 5. So from 3 to 5, we know this curve is a positive function, right? It's up above the axis, which is good. Okay, so the antiderivative is done. Yeah, it wasn't too long one. What's the antiderivative of this? X cubed over 3.
I already forgot this stuff.
Yeah, I do remember. So that's 2x squared over 2, or just x squared, right?
Plus C.
Okay, no. So, you see, you want to do one with 0. We'll do one with 0. So the area of 5 is f of 5 minus f of 3. Right? I mean, we're looking back. If you put a c in there, you just add it here, subtract it here, it'll be gone. Okay, so f of 5. Well, 5 cubed, 125 over 3. Plus 5 squared. Minus, and I better put down a set of brackets, right? Because we're evaluating two things here. So 3 cubed. Oops, 27 over 3. Oh wait, that's just 9. Plus 3 squared, 9. Okay, so we need 3's. 125 over 3 plus 75 over 3. 9 plus 9 is 18, which over 3 is 54 over 3. So 200 minus 54 is 150 minus 4 is 146 over 3. Units squared, square units. Okay, fit. There's your curve. Got the antiderivative. We want 5 to 3, so the area of 5 is f of 5 minus f of 3.
Yeah. So not that like find like those sums or
No, yeah, no, yeah, right. Remember that? Yeah, we don't want to do that way. Okay, let's do y equals e to the 2x from 1 to 2. So f of x is e to the 2x over 2. And you said you didn't remember any of this stuff. Okay. Now, you always check this, right? You check this by finding the derivative, right, which would be e to the 2x times 2, which will give you e to the 2x, okay? So, you know, it's like factoring and foiling, right? So if you find the antiderivative, take the derivative, make sure you get the... So a of 2 is going to be f of 2 minus f of 1, which is e to the 4x over 2 minus e to the 2x over 2, which could be e to the 4x minus e to the 2x over 2, or e to the 2x.
why is there still an X?
What? Oh, right, sorry. E to the, yeah, you're right. E to the 4 minus e to the 2, or e to the 4 minus e to the 2 over 2, or e to the 2 over 2 times e squared minus 1. Any or all of the above. All equivalent. Okay. Two more. Little trig. We did an E. Let's do a trig.
It's pretty good. No. They've got that momentum.
So determine the area below cos x and above the x-axis from 0 to 2 pi. So this we should probably sketch out because we know that part of this is above the x-axis and part of it's below. We got to figure out which parts are where. So what does cos look like? So there's cosine curve. So there's 2 pi. There's pi. There's pi over 2. 3 pi over 2. So we can see that we want to find this area and this area. Which are symmetric areas, right? I mean, they're the same size, so if we just find one of them and then double it, that's good enough, right? So since the areas are symmetric, we have two symmetric regions. So let's do, y equals cos x from 0 to pi over 2 and double it. Okay, so what's
Isn't it from 0? Oh, I see.
Yeah. So what's f of x? Capital F of x. Big F. The derivative of what gives you cos x?
Minus.
How about just plain old sin x?
Oh, yes.
It's the other way around.
Yeah.
So it's cos x. If it was sin x, then it would be minus cos x. Okay, so we want the area pi over 2, which is f. So we want the area from pi over 2 to 0, which is sine pi over 2 minus sine 0, which is 1 minus 0, which is 1. And so the area we want is 2. Okay. Alternatively, you could have also done area of 2 pi, 3 pi over 2 to 2 pi, right? And figured that area out. We got the same thing.
Is this formula on the formula sheet?
I don't know if we do a formula sheet.
Yeah.
I don't know, it's a tough one. The area B is B minus A. Don't worry, there's yet another way, but we're almost, but not quite there.
But then you have to time it 2 pieces.
So the answer is probably no, but wait.
Today, no. No. Yeah. I said from the start of the season and never changed.
Okay, so the area between the curve, y equals 25 minus x squared and the x-axis. Right, above the x-axis, below the curve. So pretty much this area, right? I mean, because what we're going to do is we got to figure out what are the zeros, right? So we need the zeros, so let's do that. So we need the zeros. Okay, so 0 is 25 minus x squared.
So plus and stuff.
X squared is 25. X is plus or minus 5. Okay, so we weren't asked to find, I mean, we could have been asked to go from, like, 1 to 3 or whatever. That's fine, that's above the axis, right? But we're asked a more general, above the x-axis, below, so we have to figure out, well, where do you meet the x-axis, right? In other words, what are my boundaries? Okay, big F of x is 25x minus x cubed over 3. Right, just applying the anti-power rule, which there's no such thing as, but if there were, then that would be it. And a of 5 we could also see that it's symmetric, right? You could always do 0 to 5 and double it. Okay. You'd have to make some note of that. It's symmetric about the y-axis, so I'm just going to work out the area from 0 to 5. But this won't matter. Okay, so put a 5 in there. We get 125 minus 125, 5 cubed over 3, minus, and a bracket, and we get negative 5, so that's negative 125 minus, well, it's going to be what? Minus, negative, what's that going to be? Another 125 over 3?
Yeah.
Yeah.
Oh yeah.
Right. Plus. Yeah, plus. There we go.
What do you think?
I don't know what I'm. Okay, so what do we get? 125 minus negative 125.
Yeah, it's
250
plus. Or I can get minus 250.
minus
Yeah.
250 over 3.
Yeah.
So that's 750 over 3 minus 250 over 3, which is 500 over 3. Right? Boom, done. Done.